So our first, so today's session is about like high rate quantum error correction code. And our first speaker is a Professor Kenta Kasai. He's going to talk about quantum LDPC codes with classical design principles.
Thank you. Good morning. Thank you very much for kind introduction. I'm Kenta Kasai from Science Tokyo. I'm very grateful for inviting such a nice place. Okay, so this slide states that the goal. We want to bring the classical LDPC design principles into quantum CSS LDPC code construction. So in classical LDPC design, useful node includes calm weights and low weights and randomness and girth and distance. The question is how much the freedom can be kept while HX and HZ satisfy the CSS orthogonality. So this is the central tension of this talk. The classical style freedom inside the algebraic orthogonality constraint that makes the stabilizer checks commute. So the classical LDPC codes are highly matured. So they are used in the mobile phones, internet, and magnetic recording, the SSD device drive, or everything where you use information. So our goal is to bring up the classical LDPC code design into the quantum settings. So this is the typical error rate curve for finite length classical LDPC codes. The horizontal axis represents the physical channel error rate, and the vertical axis represents the frame error rate. So this slide separates the waterfall and error flows. The error flow is steep, this one, and while the error flow is gradual. The waterfall is a region where the macroscopic behavior of the BP decoding appears. When the channel noise across the BP threshold, the ensemble level BP trajectory changes, and many variable can remain unreliable. So you can pause me and you can ask questions if you want. The error flow is different. It's dominated by a rare small structure of the graph or low-weight logical operators. The central quantity for the waterfall is a BP threshold, PBP. It's predicted by a density evolution. Density evolution tracks the BP messages for a random LDPC ensemble in the infinite length code length limit. In that limit, if we follow the edges reached by a fixed number of BP iterations, the probability of seeing a cycle goes to 0 as code length n grows. Therefore, the local computation behaves like a message passing on a tree. And BP can be described by a deterministic recursion. Okay. The key design variable for calm weights and the low weights. Calm weights is the number of ones in the column of the parity check matrix H, and the row weight is the number of ones in row in the matrix. Changing the weight changes the BP threshold, hence the waterfall location. So changing the calm weight and the row weight of the parity check matrix, that changes the where the BP thresholds are. So, and distance, girth, and the trapping set mainly control the error flows. error flows are mainly dominated by the small structure of the harmful small structure of the Tanner graph. It's called the trapping set. And of course, by minimum distance. So this separation is one reason classical LDPC code design is powerful. Different knob control different parts of the performance curve. Okay. The formulas on the right expresses this separation. The waterfall terms and the error flow terms, and the one of the waterfall terms describe the macroscopic BP scales, while the error flow terms comes from the rare constant size structure. So this is why I separate the two regimes before discussing the quantum construction. They ask for different kinds of design control. The waterfall region is approximated by this exponentially drop of the error rate. So while the error flow is approximated by a polynomial of the channel parameter P with a number of the number of the harmful small structure in the Tanner graph and its weight. Okay. So this slide gives the geometric picture of the density evolution. So in the infinite length random ensemble, consider the neighborhood explored by a fixed number of BP iterations. As the code length grows, the neighborhood contains no cycles with high probability. So the BP message behaves like as if they were passed on a tree. The recursion means that one number summarizes the typical BP messages quality after each iteration. So below the BP threshold, the trajectory moves towards zero, so BP succeeds asymptotically. Above the threshold, the non-zero fixed point appears and trapped the trajectory. Thus, the BP threshold is a boundary where the BP changes from convergence to non-convergence to zero. At the threshold, the curve touches the diagonal by tangency. So this geometric picture turns a decoding question into a fixed point question for LDPC code ensembles. Okay. So density evolution gives us the trajectory of for each iteration of the BP decoding. So xt is remaining rate of the incorrect bits at the tth iteration of the BP decoding. And if fp gives the next round the decoding rate. So when the window trajectory window opens, the BP trajectory converges to the zero. But if the channel parameter P is above the BP threshold, the window closes the trajectory. It's trapped with some certain point. So this is why in the waterfall region there are big error in the proportional to the code length. Okay, and here the density evolution, which is the analytical tool developed in the classical coding theory, Here the density evolution is used as a benchmark before imposing the CSS of orthogonality. Given the calm weight and row weight, we randomly construct parity check matrices and look at the BP threshold in the infinite length limit. Okay. This is exactly the kind of result provided by the density evolution in classical LDPC design theory. So this is not a valid construction yet, valid construction of CSS code yet. It's a reference for the waterfall behavior we would like to preserve. The horizontal axis is the BP threshold, and the vertical axis is coding rate. The main point is that the calm and the row weights move the BP threshold. If we change the calm weight and row weight, the changes the threshold and the coding rate. The plotted points also show a simple trend. As the calm weight increases from 3 to 4 to 5, the BP thresholds become slightly worse. The higher calm weight creates more edges, so it becomes harder to avoid small cycles that degrade BP performance.
Question.
Okay.
But
yes.
The column weight J equals 2 is much the worst.
Yes.
So behavior doesn't seem monotonic.
Yes, yes, I can explain it with the density evolution trajectory. It gives when the calm weight equals to 2, the slope at the 0 point has a positive gradient. With calm weight 3 or above, the slope is the gradient is derivative is always 0. So it opens, the window is always open with the calm weight 3 or above. So this is the one of the reasons. Yes.
So 2 and 3 and above are like kind of different. 2 is kind of exception.
Yes, okay. 2 is a very special one. So choosing the calm weight 2 is a bad choice. So we need to choose a calm weight 3 or above when you want the higher BP threshold. But in a lower rate region, the calm weight 2 is not very bad compared to the other calm weight 3 or above things. Yeah. And one good thing for calm weight 2 is it's very ultra sparse. So you can avoid small cycles, and you can the cycles always corresponding to the code word. Okay. So in other words, making the girth and minimum cycle size large. When the calm weight is large, so the making the girth and the minimum cycle size, the large becomes difficult. So this plot tells us what the performance should be possible if the sparse graph behaves like classical random LDPC graphs. So later we compare the constructed CSS code against this benchmark. The goal is not to claim the ensemble is already valid quantum codes, and the goal is to identify the waterfall target before enforcing orthogonality. So this is the distance side analog of the previous slide. Again, we ignore the CSS constraint and ask what random CSS type LDPC ensemble would predict in the infinite length limit. The horizontal axis is a typical normalized minimum distance divided by code length. And the vertical axis is a rate. For CAM weights at least 3, the random ensemble has linearly growing minimum distance. The plot shows that the CAM weight increases from 3 to 4 to 5. The typical minimum distance grows rapidly. So in classical LDPC codes, random construction already made the minimum distance large almost automatically. This is one reason classical LDPC design did not focus so much on the minimum distance itself compared with the BP threshold, cycles, and trapping sets. So this gives a distance benchmark, just as the previous slide gave a waterfall benchmark. The rest of this talk is about satisfying CSS orthogonality without losing these classical style guides. Before imposing,
okay. Can we go to the previous slide?
Okay.
So here, I think what you're saying is that from the BP threshold perspective, larger column weight makes BP threshold worse, while in the distance case, it looks like larger column weight is getting better.
Yes.
But the BP threshold is a threshold. I mean, below the threshold, how it's getting suppressed depends on the distance, isn't it?
Yes.
So, and when it comes to actual computation, I mean, if distance is a crazy large, then maybe what we care is the PBP, not the distance. But if distance is like moderate, then we also care how it scales after the BP threshold, right?
Yes, completely right.
Okay.
Okay. So, okay, and before imposing the quantum constraint, we therefore have two guides, one for BP decoding and one for distance. Good construction should try not to destroy either guide. Okay. So this slide contrasts the classical and quantum design object. Classically, we design one sparse parity check matrix. Tuning count and row weights, randomness, and girth, and the distance, and the trapping set. For CSS codes, we must design two sparse graphs, HX and HZ. So in this slide, we describe the transpose as a prime. Or too much algebraic rigidity can destroy the randomness, but too much freedom breaks orthogonality. The goal is the middle ground, guaranteed orthogonality with enough sparse graph design freedom. So there is also an empirical lesson from the LDPC design. When we impose too much visible structure into the parity check matrix, performance often degrades. So injecting randomness tends to improve the BP performance, especially in the waterfall region. The difficulty is that a local choice on the X side can restrict the Z side. This coupling is what makes quantum LDPC design different from the classical case. Okay. So before the construction, so let me recall the distance definition. Classically, the minimum distance is the smallest non-zero vector in the past all checks. For a CSS code, distance is the smallest non-trivial operator. So passing all checks is not enough because the stabilizer must be excluded. So therefore, the construction is dangerous if it creates a low-weight vector that passes the active checks, but it's not stabilized. This is the issue in the next slide. So quantum distance is not only about the kernel of the one matrix. It's about the kernel after consciating out the stabilizer law space. So this slide introduces the bicycle code parent construction. So starting from the two sparse square circulant matrices, A and B. So they define the parent matrices H hat X and H hat Z. So since the circulant blocks commute, the parent matrices are orthogonal. So the displayed product means that this parent pair automatically satisfies the CSS orthogonality condition. So the actual code uses only the top M rows in the parent matrix. So these top rows become the active check matrices HX and HZ. Orthogonality of HX and HZ is inherited from the parent product. So this is clean construction, but the next slide shows the distance problem. The construction is attractive because the active CSS orthogonality is automatic. The cost is that unused parent rows still remember the full parent orthogonality. So that hidden memory of the parent matrix H hat X and H hat Z is what we will show up at latent logical operators.
Well, why do we go from parent matrix to the active matrix?
So this is from the construction of bicycle code. So you don't need to use this parent construction, but it's easy to control the calm weight and raw weight, especially on the Hagiwara-Imai construction, where I will explain in I think the 2 slides later. The problem is that the latent row can become logicals. The parent matrix H hat X and H hat Z are split into the active rows and the latent rows. So this is a parent matrix and active rows and latent rows. The active rows from HX and HZ, while the latent rows are kept as not kept as checks. Because the full parent matrix H hat and H hat X and H hat Z are orthogonal, the latent rows automatically pass the active checks. So if they are not active stabilizers, they can become non-trivial logical operators. So their weight is controlled by the raw weight. So the minimum distance can be small because we are using the LDPC codes. Thus, the same mechanism that automatically gives the parent orthogonality can also automatically create low weights logicals in the active codes. This is why the full parent orthogonality is too strong for our purpose. So it imposes more orthogonality than the active matrix HX and HZ actually need. Okay. The design principle is active orthogonality only. We require orthogonality between the active HX checks and active HZ checks because that's exactly what CSS needs. But we don't want full parent matrix. We don't want full parent orthogonality. The latent row should not automatically pass all active checks. The latent-based distance shown on the slide measures where this obstacle has been controlled. So this is the definition of the latent distance. So it's included it excludes the row of the it's restricted the definition of the normal minimum distance on the row space of the latent rows. So the distance intuition is important here. The randomly constructed sparse code should have large minimum distance. This is from the lesson of the randomly constructed classical LDPC codes. Therefore, if the only visible small upper bounds comes from the latent rows, the main task is to break the latent upper bound structure. So once this latent structure is broken, the remaining code should have more like a random sparse code. So the minimum distance should become large again. So the shift is this. The design, only the active part to be orthogonal, and keep the unused parts sufficiently incompatible with the active checks. So this keeps the necessary orthogonality, but avoids the forcing latent rows to become logical and of the active code. This is the guiding principle behind the construction that follows. So in short, we want exactly enough orthogonality for stabilizers, but not so much on the unused row becomes dangerous.
Can you explain what latent distances are for? So can we go with the previous slide?
Mm-hmm.
So here in this search,
mm-hmm.
Which part is random and which part is
we want the HX and the HZ as random as possible.
Right.
And from the parent construction, so it has the latent upper bound. So what we want to do is to break the upper bound, and the rest of the remaining code is hopefully random.
Okay.
Okay. So in the classical LDPC setting, once the code is constructed, randomly constructed, it has linearly growing large minimum distance. But even if the party check is the sparse, but in the CSS code setting, we must satisfy the orthogonality, and it gives rise to the latent upper bound. So the difference is only the latent upper bound. So we can construct randomly the party check matrix HD and HX and HZ and make it sparsely. But the latent row is only the latent upper bound is the difference, only the difference between the classical and quantum settings.
And you want to make latent upper bound to be as large as possible?
Yes. So this latent distance measures the risk of the minimum distance, which stems from the latent upper bound. So it's restricted the measurement where this latent minimum distance measures the minimum weight restricted to the row space from the latent rows. If you exclude this part, so it's identical to the normal minimum distance definition.
Active partition matrix, like almost polar. It's sort of like excluding the the negation of the latent distance. You're like, well, for example, with that, like when HX and HC is like has like 1 or 2 rows, it doesn't really make sense, like, right?
You
define the latent.
You are assuming that this active part is small?
Like the row size of like when HX and HC is.
Mm-hmm. So it's very high rate code, right? So when the row size of the active part is small, that means the latent part. Yes. So the coding active coding rate is very low, and yes, but it's also upper bounded by the low weight of the latent rows.
I feel like the latent distance will capture the actual distance. Assuming like HX and AC is at 4 maybe close to 4 maybe.
So yes, if it's full rank, the rate would be 0.
Well, but if you just take that rate part, you should have finite rate, right?
Yes. So I've given an example with a concrete construction in the 2 slides later.
How is this latent distance is like close to the actual distance? Like how do you
so the latent distance measures the risk of the latent upper bound. So I have not considered when it's coincide with the actual minimum distance. So we have to consider to evaluate the true minimum distance. We have to consider the true minimum distance. So this latent distance just only measures the risk of the latent upper bound. So this is the construction I propose for this study. So this construction is based on the generalized Hagiwara-Imai codes. The point of this page is left and right Bloch circulant structure. We have Bloch circulant structure here and Bloch circulant structure on the right side. For the column weight 3 and the column weight row weight 12, the column weight J equals to 3 and row weight L equals to 12. We prepare the 6 permutation blocks permutation matrix F0 to F5 and 6 other permutation matrix G0 to Z5. So each Fi and Gj is a binary permutation matrix of size P. And in the experiments I show you later, P is chosen to be the order of the several hundreds. So in the parent matrix H hat X, the left half is made by cyclically shifting the Fi blocks, and the right half is made by cyclically shifting the Gj blocks. The parent matrix H hat Z has the transpose partner pattern with GJ blocks on the left and FI blocks on the right. So because both halves are block circulant, the product of the two parent matrices also block circulant. So this is the parent product, and it's again the block circulant matrices. So the orthogonality calculation does not become one large arbitrary matrix calculation. It reduces to the checking one block psi r for each cyclic offset r. So the term, so this is the product, the parent product, and each building block is psi r. Psi r is the sum of the fu gr minus u plus gr minus u plus times fu. So this term can be viewed as a commutator over the binary field. So if the two permutation blocks commute, fu and gr minus u commute, two products are identical and canceled each other over the binary vector matrices. If they do not commute, so this term remains non-zero. Therefore, each psi r is controlled by which Fi and Gj pairs are made commutative. The horizontal line separates the active rows from the latent rows. Only the active part must vanishes for the CSS orthogonality. This is the parent active part, active product. So in the conventional Hagiwara-Imai construction, the blocks Fi and Gj are chosen so that they are all pair commute. So then all the commutator blocks vanishes, giving the stronger parent orthogonality than the active code actually needs. So this also makes the latent rows pass all checks, and the minimum distance is upper bounded by the latent rows, which means low weight L.
So you choose that F and G to be commutative?
Non-commute. We want some of the pairs of the F and G commute, and some of the rest of them are uncommute, non-commute.
So you want that upper left corner block to vanish.
Yes.
And you need that minimal amount of commutativity between F and G to make that upper block vanish?
Yes.
Okay, I see.
So here we impose the commutativity only on the Fi and Gj pairs that contributes to the required active psi r blocks, the upper left. And the remaining pairs keep design freedom and help avoid the latent row upper bound problem. So this slide explains which commutator should be zero and which one should remain free. The left matrix is the product of the parent matrices divided by the horizontal and the vertical active latent split. The upper left region is the active product. So this is part that must vanish for the CSS orthogonality. So for column weight 3 and row weight 12, the upper left active constraint contains psi 0, 1, 2, 4, 5. Importantly, psi3 does not appear there. So therefore, we need to make only these 5 psi-r, psi0, 1, 2, 3, 4, 5, the vanishes, while the psi3 can remain non-zero. So the expansion of the psi-r is shown in here using the commutator notation. So here, the square bracket Fi_Gj means the Fi times Gj plus Gj times Fi, so over the binary field. So for the psi-r is the sum of the commutator for the pairs whose indices added to 0 modulo 6. So the important notation is gamma. So gamma is a set of Fi and Gj pair that we force to commute. In that table, C remains the label C means that the pair belongs to gamma. The C entries are exactly the pair needed to make the active log psi-r's vanish. So we impose the commutativity only on the pairs in gamma. The blank entries are unused freedom. So keeping them free helps avoid the latent row problem. Okay. So this slide compares the circulant permutation matrix and the affine permutation matrix and the general permutation matrix. So CPM has a strong algebraic control, but limited randomness. They all commute, so they are useless for our purpose. So GPM have a maximum randomness, but commutativity and cycle check becomes hard. So APM sit in the middle. They are affine permutation matrices, so they are given more randomness than the CPM, while preserving the modular arithmetic checks. So this compromise why we use APM here. APMs are therefore a representation choice. Sparse and checkable, but still more flexible than the pure circulant blocks. So with using the APM, we can control the commutativity and the non-commutativity between the two APM matrices. So this slide gives the two arithmetic checks for APM. First, commutativity. And APM is an affine map on the index set. So two APM commute exactly when the modular condition shown on the slide holds. So this so assume we are given the two APM matrix with defined by two affine maps, Fx and Gx, and Fx is defined with Ax plus B, and Gx is given with Cx plus D. And the condition for the commuting of two given affine maps is if and only if these arithmetic equations are satisfied. So it can be easily checked with equation over modulo P. So the condition means applying the two affine permutations in the either order gives the same result. The point is that we can check required pair Fi and Gi using the only APM parameters, not full permutation matrix. So this matters because P is large in the constructed example. So parameter level checks are much cheaper than the multiplying full permutation matrices. Second, the short cycle detection. For a closed Tanner graph walk, compose the APM labels along the walk. If the lifted cycle exists, the resulting affine map must have a fixed point. So if there is no fixed point, that base walk does not lift to a cycle. So for a affine map, checking either a fixed point exists is just a modular linear equation. So the condition reduced to a divisibility test using GCD, greater common divisor, as shown on the slide. Okay, so the fixed point test is cheap. And one GCD check screens each short walk before we build or simulate the full lifted graph. So thus, the APM lets us check both commutativity and short cycles algebraically while keeping more randomness than CPM. So this is the main technical reason for the using APMs. We make both constructions and screening feasible at large lift size P. Okay, yes?
If you consider like cycle in the base graph, and then like that is maybe 2D selects of that short cycle in the base graph. And then you're checking like the last cycle is lifted, surviving the lifted.
Yes. So the check is cheap because we can check in a modular P. So this slide gives a constructed example with the lifted side P equals to 768. So we obtain the girth 8, the minimum small cycles 8, the regular calm weight 3 and raw weight 12 regular CSS LDPC codes with code length about 10,000 and the coding rate is 1/2 and the minimum distance is upper bounded 48. It breaks the latent upper bounds. So the distance indicator is also important. So we have explicit 48 logical operator. So the latent distance is exactly, we proved the latent distance is exactly the 48. So that means the code breaks the latent upper bound. It upper bounds have been upper bounded with the conventional construction. So just okay, and so we don't we cannot say anything about the true minimum distance, but it only is the upper bound the minimum distance. So the true minimum distance could be 10 or 12. So, but we have observed no logical failure on the huge amount of the experiment and very vanishing error for us. So we believe that the true minimum distance is likely near the 48. So this is the factor graph used in the BP decoding. I'll skip this explanation. Okay, and the decoder is based on the fact that the BP usually works well, but very rarely, for example, roughly once in the 10,000 trials, BP can fail to converge. So in such a failure, the decoding often is often trapped by a small harmful structure in the Tanner graph. The idea of the post-processing is to remember these harmful structure in advance, and we enumerate the small elementary trapping set patterns that can trap BP and store them in the ETS library. So by then, when BP gets trapped again, we look at the remaining unsatisfied checks. We compare their pattern with the entries in the ATS library. If the unsatisfied checks match one of the stored ETS candidates, we can identify the small suspect set K. The formula on the side means that after the matching step, we do not search over the whole code. So we solve only on the residual problem inside the suspect set K. So in this way, the decoder turns a rare global BP failure into the small local correction problem. So BP does almost all the decoding, and the ETS library is used only to repair the rare failures caused by a small graph structure. And also, of course, we use the OSD decoding, post-processing after BP decoding. So this slide shows the performance result of the GAR-8 regular codes with CAM weight 3 and row weight 12. The decoder is joint BP plus processing with ETS library. And the curve reaches frame error rate 10 to the minus 8 at the physical error rate P equals to 4% over the depolarizing channel. Over the code capacity model. The density evolution threshold and the Hassing bound are shown for the reference. The first, the many weight 12 degenerate errors are corrected. Second, the BP curve aligns with the density evolution benchmark. For a cycle-free random case. Non-orthogonal codes with the same CAM and row weight. This is the prediction from the classical LDPC code design. The benchmark line is the connection back to the classical LDPC code. And we can achieve the deep error flows and the steep threshold, BP threshold near it, and its approaches to the density evolution benchmark, and also for the hashing bound.
What about the error mode here?
Error mode?
Error, yeah. What kind of error?
A depolarizing channel.
Just to do like code capacity or?
Yeah, code capacity. So the main message is the classical design principle can remain useful in the quantum LDPC construction. First, CAM weight and row weight determines the BP threshold. Second, the APM gives the randomness while keeping the algebraic control commutativity and short cycles. Third, with the joint BP and post-processing, the observed waterfall approach the classical sparse benchmarks. So the answer is cautiously positive. We can keep the useful classical design principles if we impose only on the orthogonality constraint we actually need. So that's all. Thank you for your attention.
So what is the weight of this QC code you showed in the previous slide?
Wait, me, row weight, the stabilizer weight?
The check weight.
Check weight is 12.
Oh, check weight is 12. Any questions? Okay.
So in the instruction, you have off the rows to make rate one. Make a different rate.
Yes, my construction is limited to the coding rate equals to 1/2 or above. But in our recent papers, we propose other construction, starting from the small CSS code like 500 bits and lift by CPM. So the resultant coding length is like 30,000. So it's very big, but it's labeled here, and it has achieves the very deep error flows and the steep threshold approaching the BP threshold prediction.
Okay, thanks for the great talk.
Thank you.